Okay, so we will begin today. This was the topic that we had started at the end of yesterday's class, isn't it? And I wish to draw your attention or recall what we had earlier said about conditional PMFs for continuous for discrete random variables, right? So this is going to be very similar to that. So we recall the conditional PMFs. What did we do? We did we had some event A. What could be anything, right? We had Px given A of dot given, and here you could expand, right? The A can be expanded. This is the kind of notation that we had, right? The dot, of course, the arguments, allowed arguments, and the countable set of such arguments we call them collectively as a new omega x, which was different from the original omega x, right? So this is a conditional PMF defined for what we call new omega x, isn't it? I think I used this term new omega x earlier. I recall doing so, didn't I?
Yes.
Okay. So here also we are going to do the parallel development for this. Some given some a which can be of the form x greater than y anyway. So, but there is a major twist out here which we have to see now, right? But before we get to that twist, let me look at the general philosophy. So here, what we do, we are going to look at this conditional probability, right? The conditional probability that x is less than x. So this is what we are interested in. For some dx which is very small, positive but very, very small. So we are going to look at this conditional probability. The event A will be defined, right? We are going to assume some small positive dx. And we are looking at this conditional probability for what values of x. Again, a new omega x has to be found. In general, you have to find it, and there is no magic for doing so. You have to look at it on a case by case basis, right? So for this x element of what I am going to call mu omega x. So this must be done on a case by case basis. You cannot generalize, isn't it? And then how do we define the conditional density function? We just divide this by dx, and if you if you take only the first order term in the numerator, you would find that the ratio, like you take any derivative, tends to some finite value, which is the conditional density, right? So this f, this conditional density function f, this is the conditional PDF of x given A. I am writing it on top, maybe not the best thing to do, but I don't know what else to do out here. I started writing, so maybe I'll write it here just so that it's for the camera. The conditional PDF of x given A, in quotes, is what is this fx given A of x. Then I could expand it if I wanted to. Now the reason for putting the subscript is again very clear, right? Exactly like here. You need a new subscript because it's a new PDF. It's not an old PDF. So you need that. So this is going to be basically I will suppress the limit, right? I am just not going to put that. The limiting is not something that we are going to do very seriously. So I am just going to say is roughly this probability, that conditional probability out here. I am not going to repeat all this. Just take this whole thing and put it here, divided by dx. This is a conditional probability, right? Remember, there is a conditioning by A here. So it is a conditional differential probability. That's how you have to understand it, right? Examples of A would be, for if you had only one random variable, one continuous random variable, just like in the discrete case we could consider some a has to be say x greater than x naught, for right, things like that. So with just one, with just x alone, no y or no other random variable around, so we eg of a is what? The standard example, x greater than x naught. So this kind of conditioning happens when you look at lifetimes, for example, right. Supposing capital X represents the time to failure of some device, and obviously such times to failure are always non-negative, they are never negative. You turn on the clock when you switch the device on, and we are assuming that we are only looking at when the device is on. Sometimes the devices are on all the time, like our human bodies, right. The clock starts ticking when we are born, and then positive after that. But for other models you might consider only looking at the x when you actually keep the device on. Anyway, that is not very important. So let us assume that the device is running. Then what does this event mean? X given a, given that x is greater than x naught, what does that mean? That means that what in English? That means the device is worked until x naught, at least x naught. So you are assuming that the device is worked up to x naught, and now you want to recalibrate, right. Supposing you had so the original PDF of x could be the time to failure, supposing x was the time at which the device failed, we died, right, to be very stark and blunt about it, right. So ouch, it's okay, these keyboards are coming in the way. Okay, so so x could be a time to failure for x of some device. These times to failure are always modeled as continuous random variables, never discrete, because you are assuming that you can measure the time precisely, very very precisely, and it is not from a countable set, right. So x is this. So fx is what? Fx by itself is the a priori, or just call it prior, the prior PDF of this time to failure. So what is this fx given a? This will be the posterior PDF given that for this particular a, that is for a x greater than x naught, which I can put out here, right. So this could be posterior given what? Given that device has worked up to x naught. So what is the new omega x obviously in this case? If you know that it is worked up to x naught, obviously the new x naught is x naught, it has to be x naught to infinity, assuming that the original omega x went up to infinity. If the original, if you knew for sure that the device is not going to work beyond a certain time frame, then obviously you cannot condition on an event which is impossible, that is put x naught bigger than that time frame, right. So in all of this we assume that this event conditioning on this event a makes sense. Otherwise the conditional probabilities and conditional PDFs, nothing makes any, cannot be calculated. So in other words, this P of A, right, has to make right, it's something funny, as we will see. We will normally assume that this P of A is greater than 0 for any conditioning event, but there is a twist to that, we will come to that. But anyway, at least for now, for here, definitely for this kind of thing you want this to have positive probability. This P x greater than x naught must have positive probability, and then you can, I will give you a formula here, we will look at this. So fx of A, we know that this fx of A of x given this x greater than x naught is basically going to be the same fx of x divided by P of x greater than x naught for small x greater than equal to x naught, whatever. This is P of A, which I am writing in expanded form. I do not want to write as P of A, I am writing it as P of x greater than x naught. this is exact. Why can I make this statement? First of all, is this a valid PDF? It is a valid PDF. I am only going from x0 to infinity, and I am claiming that this operation will exactly give me this. Does anyone have any problem with that? Yes? This operation here, that is to take x between x plus dx given a. Okay, how do we resolve this? You write this as the probability that x is between x and dx given and a divided by the probability of a. But it turns out for x greater than x0 that the probability of b given a, b will be a subset of a. That x to x plus, this is b, this b is going to be a subset of a for x is in this case bigger than x0. What is the conditional probability of b given a? B given a when b is a subset of a is just simply pb divided by pa. So what is pb now? Pb is just this probability p of b, which is f of x, fx dx, fxx multiplied by dx. This pb just by itself, forget about a. We have understood that this is going to be pb divided by pa. Pa is this. Pb is fxx multiplied by dx. So what is the ratio? This into dx divided by this, and then I am also going to divide by dx for getting the density out of it. So I will get exactly that. So if I write all this on the board, it going to take too much time. So I assume that by now you have developed enough intuition that you can fill in all the missing details out here. So this is an interesting expression which if you evaluate it in particular for the exponential density function, parallels what we had for the geometric PMF. It becomes memoryless. In other words, for the if you say that the time to failure is the exponentially distributed, which is itself a highly questionable statement anyway, it turns out that that this conditioning is just simply shifts the whole density function to x0, otherwise doesn't change it. But I'm going to leave that to you to actually just simply plugging in the formula here. I don't want to actually do it, right? You can do it. I think maybe it's part of the homework also. So this kind of conditioning can also obviously be applied if you're looking for finer events. That is x could be in some interval instead of some finite interval, right? Instead of infinite interval. It's exactly the same thing. So let's go beyond this, right? Supposing now we want to do it for two random variables. So I'm going to keep up to here and erase from here on downwards. Is it okay? Up to here, whatever I've said, and erase all this. By the way, let me also give you motivation for studying conditional PDFs. They are the basis of what we will study later on as conditional expectations, which are very, very important for many applications. Right? So unless you understand conditional PDFs, you cannot understand conditional expectations. Right? So this course is highly packed in that sense. Right? First half of the course we study just PDFs and PMFs, and then the second maybe little more than half, the second portion we bring in expectations and do the whole lot together. So at that time we will be dealing a lot with conditional expectations. So at that time all of this will be, understanding of this will be very important. Right? So now let us say we have two continuous random variables x and y. So given two jointly continuous, so now we have a plane instead of just a line, and we can think of conditioning events like x greater than y and so on, which have positive probability like we saw yesterday. Or we can think of actually saying, well, I have observed in some experiment that y took some value, why not? What does that mean? Obviously, right, you measuring y to some precision, and let's say that to that precision you have you have observed y equal to y naught. So somebody makes a statement, so A be defined as y equal to y naught. right. And you might say, is this a event with with non-zero probability? The answer is, well, it has vanishingly small probability, and this kind of thing, the conditioning always means what? To be interpreted as y naught less than y in some sense, y plus dy. If you don't like, I mean, this is the easiest way to write it. You can also write it with a symmetric interval if you want. It does not matter. This is only right one. The simplest way I put the dy all completely to the right of y naught. So this is my meaning of this statement. The meaning of the way I am going to interpret this. After all, y naught has to be measured to some precision, and some imprecision in the measurement of y naught, I am going to write it like this. So y naught is actually one of the possible values of y. It is not an impossible value. So this event will have a vanishingly small probability, which will be the density function of y at y naught multiplied by dy, isn't it? Now can I talk of the conditional density function of x, PDF of x given y equal to y naught? How do I go about calculating this? So let us draw a picture and try to see what's right. Let us assume that I am let us consider only the first quadrant, otherwise drawing becomes a little messy. Let us assume we have, right, we are starting with the only this being omega xy. Okay, so what I have said is y is between, so the conditioning event is out here, y to y, y naught to y plus dy. So y has taken a value here, which means this entire strip is possible somewhere, right. We are living only in that strip. Then I am considering the probability that x is between x and dx, given that y is between y naught and y naught plus dy. So I have to draw, let us say my new dx is my new omega x that found independently. Let us not bring that into the picture right now. Let us assume that this x is inside the new omega x also, that it makes sense to look at the density of x at this point. So I have x here and I have x plus dx here. Okay. So what do I want to calculate? I want to calculate the probability of, I want to calculate this probability. So this implies that probability, let me write it in full here, x is less than x less than ex, given that, given a, I will write it as a. This is, now this is no longer a subset of this. If you just look at this event, it will be this whole vertical strip. This b given a, b, in this case now b is not a subset of a. Earlier in the what we rubbed out, b was a subset of a, but now it is not. So we have to write this as comma a. But now I will expand a. If I expand a, how do I expand a? I expand it like this, y naught less than y less than y naught plus dy, divided by what? Probability of a, which is so it turns out that the numerator is exactly this portion, the probability of finding xy in that differential rectangle. So this is a and the way I have done the coordinates is that this bottom right point is my x comma y naught. This x comma y naught is this point out here. Right. I am taking dx and dy both to be positive. I mean, it does not really matter at all, but that is just the way I have done it here. No matter how you write these intervals, it turns out the numerator, if you take dx and dy both to be very small, is going to be what? In terms of the joint density function, how will we write it? It is, go back to your 2D calculus, right. So this is the volume, the probability under a, in some small differential rectangle, and you can assume that the joint density function is reasonably constant over that whole rectangle, which is going to be true in the limit as you take both delta x and delta y both dx dy both going to 0. Eventually we are going to do that. Right. This dy also we are going to make arbitrarily small eventually. We are keeping it finite just so that we do not divide exactly by 0, but once we cancel off the dx's and dy's, we can, it does not matter, right. That is how we did differential calculus very first time you saw it. You may have wondered what the hell is going on, but now I hope you have seen it enough number of times so you do not, right, so you do not find it too wacky. But basically it is going back to the nuts and bolts of differential calculus. So what is the numerator now? The numerator is essentially fxy evaluated at x comma y naught into dx into times dx times dy roughly. So I should put not exactly equals but roughly. What is the denominator? The denominator is what? Fy of y naught multiplied by dy, right. And happily the dy goes is exactly the same dy, that is very important. So when you deal with differentials, you have to know that you are dealing, you can cancel the differentials only if they are the same thing, right. I cannot cancel this dx, I cannot cancel that dy, right. So I can only cancel the dy if it comes both numerator and denominator. So this is like a first order approximation in some sense, which is valid or what when both dx and dy become very small, right. We are ignoring the, in other words, a higher order Taylor series terms if you want to look at it in that sense. So now what I am going to do is I am going to get the density. So this is still a differential a probability. This ratio is this, and it has a dx. It may not have the dy, but it has a dx, which is only to be expected because that, right, because this dx is here. Now the density function is that differential conditional probability divided by dx. So that will get rid of this dx here, and if you collapse it all down to 0, what are you left with? So now I can erase all of this and write the most important relationship that we need to have, so which implies that this conditional PDF, let me put desired conditional PDF, I need to have notation for this. This equals fxy x comma y naught divided by fy of y naught. It is just a ratio of joint divided by marginal, just to be like we have had all the time, except that we are only dealing with PDFs and not PMFs or anything else, right. So neither of these is a probability as we saw, but the ratio can be interpreted as yet another PDF. Remember, this is just a number. Once you freeze y naught, this becomes, the denominator is a number. So you want to divide only when this PDF is bigger than 0. So we are going to do this division here, that this should make sense, physical sense. You cannot condition on y naught if y naught is not in the range of capital Y. Makes no sense, right. It is well and truly impossible. If you have a uniform random number generated between 0 and 1, you can't ask for y equal to 2. It makes no sense absolutely, and it should never be, such things should never be done. So assume, so where I should put fy of y naught is strictly positive. So notation here, how do we write this? We are going to write this as small f x given y, and we are evaluating the PDF at x, so x is the argument given with the vertical line. Please, all givens are vertical lines, nowhere should I see, I have seen some horizontal lines in the quiz. This is the last time I am going to tell you, I do not know if you are already faithful or not, but I do not like to see horizontal lines for givens, because there is nothing to discriminate between that and a divided. So, please do not use anything other than a vertical line for given. Given y naught. So, is this notation clear? X given y, because the conditioning event y equal to y naught happens so frequently in practice that this is a, for that kind of conditioning we write like this, x given y. It means that you're going to say this whole thing PDF is a conditional PDF assume given some value of y. What value of y? That value of y is put here. So, this becomes in general a PDF parameterized by the number y naught. Y naught will become a parameter, a constant for the PDF itself, as we will see. Look at some examples, right. So, y naught is a parameter. And obviously, for different values of y naught, you are going to get different PDFs. I think this we saw in the conditional in this discrete case already. For different values of the other random variable, you get a whole family of PDFs actually if you look at all of them together. So, this is not just one conditional PDF, it is actually an uncountable number of them, because we have an uncountable number of values of y.